next in the series, that is the third presentation, is the topic is improving minimum control speed with a fly-by-wire flight control system. And we have an immensely qualified team comprising Mr. Mike Heller, Technical Fellow, Flight Dynamics, Boeing Company, and Mr. Ricardo Tavern, Chief Test Pilot, FA-18 Program, Super Hornet Demonstration Pilot, Boeing Defense, Space and Security. Well, basically, from the looks of it, as it is meant to be a highly technical topic, the concerns in main, from the synopsis, as I gathered, single engine minimum controllability speed criteria on a multi-engine aircraft like the Hornet, we are all aware, FA-18, where a rolling moment is apparently more significant rather than a more traditional yaw moment that could normally be expected in the case of at a critical stage, say after takeoff of a twin-engine aircraft like the Hornet. But the loss of control due to the reflex stick moment that the pilot would give, the kind of moment that is induced was a matter of serious concern, and that is something that they have addressed very resolutely, and they are going to be speaking to us on this topic. A few words about the speakers. Mr. Ricardo Tavern, CTP Boeing FA-18 program, inclusive of the Super Hornet and the Growler programs. He's also a renowned air show demonstration pilot and has coveted several air show awards. In-service experience of 20 years as a combat and test pilot, and he's a retired major of the Canadian Air Force. As he told me just prior to the session, he has published several papers and has been guest speaker at several occasions like this, and that we are happy that he has accepted our invitation to be here with us as a guest speaker. He has more than 3,000 flight hours in over 30 types of aircraft, of which 2,600 are on the Hornet and 800 on the Super Hornet. Mr. Mike Heller, Technical Fellow of Boeing Company, specialist in high angle of attack aerodynamics and flight control, overseen claw design and software upgrade of the FA-18 Super Hornet. 30 years in the company has seen him oversee several other earlier projects as well, and that includes a host of aircraft that his company has produced. A recipient of several significant awards in aeronautics and astronautics, and if I just go into those, probably I'll eat up the time for presentation, but very, very significant. BS in aeronautical engineering and masters in engineering management. So with this kind of qualification between the two of them, I'm sure we are in for a very fine presentation on the topic. Over to the speakers.
Thank you, Mr. Chairman. Can you hear me just fine on this mic here? Good. Mr. Chairman, if I could digress just momentarily, it's late in the afternoon, and for a little levity, I just want to say how much I enjoyed the last paper. You spoke your characters of the East and the West, and I noticed that the pilot from the East was wearing green pants and a red shirt, and that you said that this was 40 years ago, but my good friend Pavel is sitting there, and I happen to know he has green pants and a red shirt just like that, because we went out last Aero India, and that's exactly what he wore. What I couldn't believe is that your depiction of the testers in the West were dressed in black and white, and I couldn't believe that he did that. Perhaps it was maybe a little more accurate than you thought. The last thing I wanted to say about your paper was that given the population of India and the importance that India has in the world right now, I think it's high time that you invented your own coordinate system and your own axis system and then forced it upon us in the East and the West to follow. In all seriousness, it's funny the paper that we started off with talked about VMC. It's what we're going to talk about as well. As we all know, the Super Hornet is here in India at Aero India, and we are in the midst of a Merca competition. But I want you to know that as a test pilot and member of the Society of Experimental Test Pilots and a former president of the Society of Experimental Test Pilots, I absolutely insist that in forums like this, that we close the door, we put all competition aside, and amongst testers, we talk about lessons learned. And that means talking about things, not just things that went well, but things that didn't go so good. We only learn our biggest lessons when something goes terribly wrong. And so I stand before you today as a tester with my colleague here, a flight control designer and a tester, to tell you something that went wrong and to not give you a presentation on why I think the Super Hornet would be perfect for India, but what went wrong in testing for the purpose of sharing and obtaining lessons learned. VMC is a challenge in a Navy-built airplane. The nice thing is that if flying at land-based, the flying qualities for single-engine operations result in land-based operations being a benefactor of the challenges that the Navy has in flight control design. I say that because in the previous paper with the C-130, an engine cut or an engine loss after V1, after max abort speed on the runway, is a challenge. It's the worst spot for an engine loss. And yet, you still have time to get things sorted out. You can sort things out. Now, in a four-engine airplane versus a twin-engine airplane, it's slightly different. But there is time to sort things out, even when the engine cut is at the worst possible moment. In a Navy-built airplane, they would argue that the worst possible moment of an engine loss would be maybe a couple of frames before this picture's taken. And you can see that there is no time and no chance to get anything sorted out. Single-engine flying qualities have to be suitcased immediately, and knowledge of VMC and flying qualities have to be very well known at this moment, because you don't have time to change things, to sort things out, or to gain speed, or to do anything like that. Let's immediately jump into VMC testing and how we do VMC testing at Boeing Company and how we did it on the Super Hornet. We use a technique or a term we call dynamic VMC testing. It's something that is not taught at the test pilot schools, at least when I went through Air Force test pilot school in Edwards, and then later when I instructed at the Navy test pilot school, we didn't teach this technique. Typical VMC testing of any airplane is pretty basic. Reduce the power on one engine, go to full power on the other engine, and just start to slow down. Slow down very incrementally, slowly, slowly, slowly. And at some point, you feel the airplane rolling off, or you feel the yaw come on, and now you know you've reached VMC. Pretty straightforward. That is what we call static VMC testing. And while you obtain an answer, which is based on the forces and moments on the plane, it doesn't necessarily represent exactly how engines are lost operationally when it really happens. What really happens is the pilot's taking off, everything is good, or maybe the airplane is going on the catapult and everything is fine. There is suddenly a catastrophic loss of thrust. The pilot gets a warning, he looks inside. There is some duration of time. Things start to go wrong, and now the pilot reacts. That's really how it happens. And so we designed a test technique for determining VMC around that reality. And so our test technique, our dynamic VMC test technique, is to first slow the airplane down to a fixed speed, get everything under control, then dynamically cut one engine idle, go to full power on the other engine, and then force the pilot to count to 2 full seconds before that person is allowed to make any inputs whatsoever. The result is that the airplane now begins to do something, okay, whether you're above VMC, at VMC, or below, something's going to happen, and then after 2 seconds, the pilot is allowed to react and now has to arrest the rates that have started, and if he is successful, then you're still above VMC. When you're not successful, then you know you've reached VMC. Well, I can tell you that we progressed through the Super Hornet VMC testing quite uneventfully. 2 rudders, great flying qualities, great engineers designing our flight controls, and we went through pretty much without any problem at all, finding out that in most cases the weight had to be reduced in the airplane to such a light weight to reach the VMC that we could even measure was such that the airplane would never ever be taking off at that weight. In fact, the fuel, you had to be so low in fuel that you were probably already RTB at that point. And so it was almost a perfect case. You know, the perfect case is an airplane that stalls before it reaches VMC, and now VMC doesn't exist, really, because the airplane would stall first. The worst case is an airplane, of course, that has a departure or VMC condition while perfectly flying and still well above stall. The other thing that complicates a fighter plane as compared to conventional airplanes is that VMC testing in a conventional airplane, you do it once and you're pretty much finished because the outer mold line doesn't change much. In a fighter plane, the outer mold line essentially changes with every configuration change. And so you have to do VMC testing clean. You have to do VMC testing with pylons, with air-to-air weapons, with air-to-ground weapons, with a mixture of air-to-ground and air-to-air weapons. And for a complete study, you should also do VMC testing with asymmetric stores and asymmetric weight and asymmetric configurations. And we did that, and it all went fairly well until we met our problem child, which was this configuration. Some of you may know that the Super Hornet can be configured as a tanker to give fuel to other Hornets. And in that configuration, we put, what's called 5 wet is the term, 5 wet stations. And so the aircraft has 4 3,000-pound fuel tanks. The center tank, which unfortunately you can't see at this picture angle, is another tank. At the front of the tank is a propeller that can turn in the wind. It produces hydraulic power, and it's essentially a Sergeant Fletcher pod. And so now we can control a hose that comes out the back of it. There's a basket, and that structure also carries about 2,000 pounds of fuel as well. And it looked like a nasty configuration. Obviously, there's a lot going on there, and so we elected to do some VMC testing of this configuration just to verify that there's no problem. I'm going to show you a test point that didn't go so good. And so just to recap, the pilot will set up on conditions at a certain weight. He will slow down to 14 degrees angle of attack, or maximum angle of attack with the gear and flaps down for this testing. And then when he's on speed conditions, cut one engine, go to max power on the other engine, count to 2 seconds, and then attempt to recover. It appears that he's pretty much recovered before things go horribly wrong. As we run the video, I guess I should warn you that what you're about to see is very graphic, so small children and people that have a propensity for nightmares should close your eyes because it's not very pretty.
Okay, idle, max, rudder. Okay. Yep, that one's not controllable. Oh, the sides look still building. Okay, come on. Come on.
Roll out. Roll out. Altitude. Altitude.
Knock it out. I'm okay. I'm okay. Still with me, Data? Still with you?
He's asking the ground station, are you still with me? Even they, I think, were all chin on floor sort of thing, completely shocked at what happened. Forgive me for not explaining it, but I think everyone as a tester in here could probably figure out the heads-up display fairly quickly. The initial conditions were 2,000 feet. We try to do VMC testing as low as possible to the ground, and so 2,000 feet above the water, he departed controlled flight. If it looked like water straight down, it's because that was water straight down. And then he recovered. If you looked at the altitude, it actually went to negative numbers. And the only reason it went to negative numbers is because we fly 2,000-foot pressure altitude. And so he had the altimeter set to 2992. And on that particular day, the pressure of the atmosphere was such that he actually was at 2,000 and about 100 feet, and he reached negative numbers. Had the pressure been the other way around, he wouldn't have made it. And so that's how close we came to losing an airplane and to losing a test pilot in the test program, doing a very benign VMC test just like all the others, and it was a real eye-opening experience for us in the program to understand how could this happen. We probably should have seen it coming. I knew this from simulator testing. Something I'm showing you here is something that shouldn't be unique to the Super Hornet. It's actually just pure physics of any airplane. But we plot it uniquely. This is a plot you've probably never seen before. And it's VMC as a function of lateral stick deflection. And you're probably wondering, well, what does that mean? Lateral stick is used to control roll, and this is basic stuff. But lateral stick, as you know, also can cause adverse yaw from the downgoing aileron. And the adverse yaw that is caused by the downgoing aileron when one tries to correct the bank angle of a VMC engine cut, I mean, you can do it on a chalkboard if you like, but it's always the wrong direction. The adverse drag is going to exacerbate the problem. It's going to make it worse. And so we had noticed and knew that lateral stick could affect VMC because the more lateral stick one uses, the more adverse drag you have. And now as you get closer and closer to the number, you can actually make an argument that says that VMC is a function of lateral stick, something that is not in any textbook anywhere that you might read. And so we actually plotted it out. It's not a coincidence that the emergency recovery procedure of the legacy Hornet, the A through D model, if you were to lose an engine off the boat, okay, is apply max afterburner, apply max rudder pedal against the roll yaw, okay, maintain 10 or 12 degrees of pitch attitude, all right, hopefully it's going to fly away. Do not exceed 14 alpha. Do not exceed half lateral stick. It's right in the procedure. And it's been there for 20 years. Do not exceed half lateral stick. Because they knew that lateral stick could exacerbate the situation. In this particular case, the pilot also knew he wasn't supposed to exceed half lateral stick. I knew it. We all tested that way. But when it finally happened, when it finally started to roll off, the pilot used more lateral stick than half. And you can see the consequences. To dissect it now, I'll ask Mike Heller to come up and give you an analysis of just how this departure occurred and how this played a role in it.
Yes, I am the data guy, and this is how it works in the test world when we hand it over to the engineers. But what Ricardo failed to mention is the one right before this was very easily controlled. It was only about 4 knots faster, and it was very controlled. And this is the rudder deflection versus time, and this is the yaw rate. Very controllable even with max rudder. And here's the time history of the problem child. And it's not surprising that rudder pegged in both cases. The control laws do that. There's a side slip feedback. As the pilot counted 1 potato, 2 potatoes, right here he puts in the rest of the rudder, and that was to fight the side slip. The green case was yaw rate, everything was fine. The red, not so fine. Non-zero yaw rate is bad when you're 2,000 feet above the water. Gee, what could have happened? Here's the lateral stick, and here's the side slip. And side slip is the enemy. And let me click this again. Yes, he used a lot of lateral stick. It was instinctive. Side slip is the enemy for anybody who designs flight controls. Side slip adds a lot of rolling and yawing moments to the airplane and can get bigger than what the pilot can do with the surfaces. Simple as that. Side slip has to be controlled. And it was not controlled in this case due to all this lateral stick deflection. In the olden days, there was something called departure resistance criteria. These days, with high-speed computers, unlimited memory, you can sit back and let the simulator do everything. Back in the old days, there was an equation called the lateral control divergence parameter, LCDP, which was a measure of the aileron's ability to make side slip, adverse side slip, like Ricardo schooled us, and its ability to roll the airplane. And it's a balance. And when the side slip wins, that's wrong. And we clearly violated that departure when we had the hard over rudder at 14 alpha, full flaps and gear, and this loading. And if we had a little bit of foresight, we would have looked at our calculators and our slide rules and could have figured this out ahead of time. Here's the aileron deflection. Again, it got very big, and this is the right wing down, and we maintained zero roll rate to a point, and then, as you saw in the video, the airplane eventually departed to the left despite full right aileron. And we know why now is because of the adverse side slip and dihedral effect and what causes that. So, what do we do now, Ricardo?
So we had a goal. Clearly what we had was not acceptable, and we had some options. And one option was do nothing. Believe it or not, the procedure says don't exceed half lateral stick, and the pilot exceeded half lateral stick. So you could make an argument that, well, if you wouldn't have violated the procedure, then that wouldn't have happened. The rest of the test pilots in the room, myself included, were jumping up and down and saying that it's a completely unacceptable answer, that the natural thing any pilot would do, even one that is highly trained, is that as the airplane starts to go, you're going to keep trying, and once you reach half lateral stick, if it's still rolling off, you're going to use the rest of it. It's just pilot instinctive reaction. So the notion that a step in the procedure, don't exceed half lateral stick, is an acceptable one, is now out the window. And we have a graphic example of exactly why with that video. The other solution was put Mike to work with his team for a major rewrite of the flight control system that would probably take a great deal of time, money, and effort. That's probably not an option either. And the third one was, how about we think this through? How about we make a surgical fix? We are, after all, in the digital world now, and we should be able to overcome this problem. I mean, we're talking about adverse drag. We should be able to overcome this problem in a surgical way for an engine loss case and make the airplane smart enough to understand when this surgical fix needs to occur. This is a very, very simple picture of kind of how we did it, but we had a conversation that went like this, and I think it is significant. When test pilots get in a simulator and then later in the airplane and we're developing the flight controls, if you ask us, if you're a design engineer, what do we like about the airplane's flying qualities, and you have something that's programmable like a digital flight controls, we'll tell you a pretty simple answer. Give me more roll rate. I like it fast. I like to roll it fast. Get rid of the time constant. I don't like a big tau. I want a small one. I want it snappy. I want it rolling. Ask me that. That's the answer you'll get. Ask me if I want more roll rate. All I can tell you right now, yes, give me more. I'll take it all. Don't hold any back. I think if you asked Pavel the same thing, he would say the same thing. Give us roll rate. Because as pilots, we're flying an airplane that's working properly, and we want it to be good. We want it to be snappy. It turns out that's exactly what you don't want to have if you lose an engine. Because if you lose an engine, all I'm worried about, and if it happens to me or anyone, all you're worried about is living at this point. The last thing I want to do is impress someone with this great roll rate. Look how snappy my roll rate is. I don't care how snappy the roll rate is. I just want the wings to remain on this, this side, pointy end up, and I don't want to depart, and I don't want to lose control. And yet, we've just spent a great deal of time and effort designing a snappy flight control system that uses large aileron throws because that's what pilots want. And so the fix, conceptually, the conversation went like this. I want a snappy airplane when everything's working right, but the moment there's an engine loss, all I want this stick to do is to keep me alive. I'm not trying to impress anybody. And so I want this to be bank angle control, all right, bank angle control, keep the bank up when I lose an engine, but when everything is working, I want this to be roll control, and I want impressive roll control. So impressive roll control when everything's working, bank angle control when it's not working right. And the way Mike and others figured out how to deliver that to us who were doing the testing was to go into here and say, all of that stuff you see in red, all that stick deflection that you get with lateral stick, you don't need that when you lose an engine, so we're going to take that away. You don't need it. And we're going to truncate the amount of stick deflection. You can move the stick all you want, pilot. If that makes you feel good, keep going. But you're not going to get any more aileron because we know that's not helping you. It's making it worse. And so the aileron deflection as a function of stick deflection is based on what's good for you, not what you think you want to have. And they did a brilliant job. And I think you've got the next slide to say how you did it.
Yeah, this is Ricardo's favorite chart when the engineer walks through every little nook and cranny of the block diagram. And since it's almost 6 o'clock in Bangalore, we won't do that. But I did want to make the point, though, that we only had one chance to do this. It was very late in the development program, and it had to be surgical, which means only affect a small part of the flight envelope, and that's what we did. What we essentially did is made proper use of the rudder. Everybody wants the rudder. And so what we did is said, okay, if the directional axis wants it for side slip control, you have it. You can have all of it. In that case, though, we're not going to let the lateral axis have much. In fact, we're going to constrain the lateral stick so that he won't need a lot of roll coordination if there's no rudder there. And that's what we did. We also scheduled it for 12 alpha and above, and we also said, okay, if you want to go the other way where you have all the rudder, go ahead and have it. So you have full control the other way. And so that's what this logic is, and that's what we programmed. And I'm happy to say it worked the first time.
To the testers in the room who write test plans, imagine writing this test plan. We came up with this theory. We worked it in the sim. We worked it all out. We developed it. And now we have to write a test plan and go in front of management, in front of the Navy, management in front of Boeing, and say, we're going to go right back to where we just were, and we're going to put the airplane in the exact same configuration and do an engine cut at the exact same conditions and prove that this works. Okay? Getting people convinced that you can do that safely took a great deal of difficulty. This is the test point. I had the opportunity to fly it to prove that we were right. Not only was I going to wait the full 2 seconds after the engine cut and the airplane started to roll off, but instead of using only some stick, I was going to use full lateral stick input. I'm going to go right to the stop on purpose, a complete violation of what was the procedures, put the stick against the stop, and show that there is no departure sign at all at this VMC condition, and that the airplane would roll upright. You want to play it?
Okay, this will be a 14 alpha VMC point with a full lateral stick.
Slowing down to 14 alpha.
Roll off. Okay, 2, 1, idle, burner,
Okay,
1,000,
engine cut,
2,000,
burner.
recovery, and full lateral stick. Nice. Okay, nothing but a nice positive roll away from the initial roll-off. AOA didn't really budge initially. Good roll response, no sign of VMC, and no yaw tendency at all. Real nice.
Yeah, someone noticed we had one concession, and that was that if 2,000 worked, 3,000 would be better. I like the idea. I didn't need to go to negative altitude, so everything about this test point was exactly the same, except it was flown at 3,000 feet. And believe it or not, we actually flew it slightly lighter in weight because what we were trying to do is we even compensated for the difference in thrust of 3,000 over 2,000 so that it was exact test point. But yeah, we never got 2,000 back again. I can tell you in the simulator I did some very silly things, much lower altitudes, large stick throws, and the airplane behaved very, very nicely. Just to wrap up our lessons learned, training alone is not adequate when pilot is required to act against instinct. If there's something in the procedures that's against instinct, it's not going to work. I think we proved that. And if I could just take yours in the interest of time here, VMC control law mod eliminated lateral stick-induced yaw departures, and I think that was proven with this design. The surgical designs are kind of fun in electronic flight control systems because you can get in there and do some pretty interesting things. And that's our presentation.
Thank you, Mike and Ricardo, for your presentation on improving minimum control speed and fly-by-wire with a fly-by-wire flight control system And also thank you for showing those very frightening videos. And unless you actually, people who have not experienced these situations, unless they see them, it's very difficult to comprehend what you're saying. And it's always very educating. All this made possible, I guess, through modern fly-by-wire systems, computers actually cutting in at times when it is undesirable for the pilot with his instincts to try and control the aircraft by his natural instincts. And once again, in the realm of innovation, which seems to be the constant thread of the presentations that we are here sitting through. So thank you both very much.